Yeah, okay. So this is lecture 3. So this is, today we'll talk about the geometric expansion. And yesterday we saw the definition of the truncated kernel, which is KTX. It's an alternating sum over standard parabolics. So this is the definition in this, and here Kp is the kernel of the induced representation from the Levy. So it's given by the integral over NPA of the sum over gamma. Let me write gamma MPQ dn, and you're integrating on the diagonal. So in this expression for k, what we are looking for now is something like this: a sum over conjugacy classes of T KTOXF. We want something like this, where this resembles our co-compact case. So this is something like conjugacy classes, and maybe this is a weighted orbital integral here. So some orbital integrals that we want to find this. So this is what this is, and this will be in terms of some geometry or some volume of something. So this is the geometric expression is going to look like this. Expansion. So the relation here is not just in the co-compact case we had just conjugacy, usual conjugacy, but this is something different, slightly more a variant of that conjugacy. And so you recall that if you have a gamma in GQ, it has a Jordan decomposition, semisimple part times unipotent part, and they commute. So now the definition of this O is the following. So say two elements gamma and gamma prime in GQ are O equivalent if their semisimple parts, gamma S and gamma S prime, are GQ conjugate. So this is an equivalence relation here, and let O denote the conjugacy classes, or what is known as the coarse conjugacy classes. And I will also denote it by Arthur conjugacy classes. Arthur doesn't denote it by Arthur conjugacy class. Yeah. So it's finer than. So in some sense, so your semisimple parts have to be conjugate to each other, and you don't care about the unipotent part. So for example, if you are looking at the identity element here, so one of the gamma is identity, you cover the entire all the set of all unipotent elements in that case. Okay. So there's a bijection here. Between O and semisimple conjugacy classes. Where by semisimple conjugacy classes, I mean take all semisimple elements in GQ, and the relation is just usual conjugacy on them. Okay? And how do you go from one to the other? So you take some little O, and then you map it to gamma, where gamma is the semisimple part of any element in O. And this relation here is just usual conjugacy. Are you following? So take an O, take any element, pick any element in it, look at the semi-simple part of that element and map it to that element. Okay. So this is the relation. And then you define what is known as an anisotropic conjugacy class in the following way. So the condition is that O cannot intersect PQ for any proper parabolic circumference. Okay. So you call such classes as anisotropic. Now there is a lemma which characterizes such elements, and that it says that gamma in GQ, gamma in O, I mean O inside GQ, represents an anisotropic class precisely when the connected central, the maximum split torus in its connected centralizer means the connected component of the centralizer H is AG. In our case, SL2 case, AG is trivial. So you want that, take a gamma and compute the centralizer inside G, take the connected component of that. In SL2, it is just, you don't have to take the connected component, it's anyways connected. And then take the maximum split torus, it has to equal 1 in the case of SL2. Okay. So, so let's see some examples. The simplest example is actually GLN. So for if G is GLN, then this O is characterized by characteristic polynomials. Okay. So if you take a semi-simple element, take the characteristic polynomial, the eigenvalues decide what it is going to be. So O is in bijection with characteristic polynomials over Q. And in particular, if you take G is GL2, there are 3 possibilities of a characteristic polynomial. The first is that the characteristic polynomial let me call that polynomial as P. And there are 3 cases. Either it is irreducible, if it is reducible, it has distinct eigenvalues or the same eigenvalue. Okay. For GL2, there is the only possibility. So irreducible, P is irreducible over Q. And the second case is P has distinct roots. So this is like cosine theta, sine theta type. And D has distinct roots means it's like A, B, A not equal to B. And so this is one of the element inside O. And the other case is P has unique repeated root. In which case your element, a central element, sits inside O. Okay, so these are the 3 cases. Now let's see what these conjugacy classes for SL2 are. Okay, and it's similar but not exactly the same. So take G is SL2. And one thing you observe is that if you say take O1 and O2, and if they happen to have different characteristic polynomials, then there is no hope that they will be conjugate in SL2, right? But on the other hand, so let me write what I just said. So first is so if O1 and O2 have different characteristic polynomials, then clearly they are not equal, not in the same conjugacy. our third conjugacy class. But on the other hand, so what I'm saying is fix O in OSL2 with characteristic polynomial P. Okay. And the first case is the first case here, which is that P is irreducible over Q and splitting field is L. So L is a quadratic extension of Q, and P has distinct roots inside L. So the roots necessarily have to be distinct. And now you suppose that two elements in O1 and O2, say gamma 1 and gamma 2, have the same characteristic polynomial P. Okay. So this means that they are conjugate over GL2. So there exists, so gamma 2 is G gamma 1 G inverse. G is in GL2. Okay. Now I want to know whether they are conjugate over SL2. So does there exist an H in SL2Q such that gamma 2 is H gamma 1 H inverse? So does that exist? That's the question. Okay. Or what do you guess? So whether two elements conjugate in GL2 have to be conjugate over SL2, and that is not true. So the equivalent condition for this, this is equivalent to saying that there exists an element C in the centralizer, which I'm denoting as CENT, of GL2 of gamma 1, such that determinant of C is the same as determinant of G. And the way to see these two statements are equivalent is just by denoting that C is GH inverse. And this helps us to go from one to the other. So what I'm looking for is two elements conjugate over GL2, but are they conjugate over SL2 or not? And the condition is this. So far, is it okay? And now, this reduces to the following. So the equivalent question is, what is the image of the following map? Or the co-kernel, actually, image of, let's find out. Yeah. So determinant is the map from the centralizer in GL2 of this element gamma to Q cross. And what is the thing about Q cross? It's the set of all determinants, the image of the determinant map of GL2Q. Okay, so these are the distinct ways to go into H. So what I'm saying is, what is the image of this map? That will answer whether GL2 conjugacy implies SL2 conjugacy or not. And so since our gamma 1 element, since we are in the irreducible case, which is also the anisotropic case, so since gamma 1 is in anisotropic, this map, the determinant, this map is the same as the norm map. Because these are elements like A, B, B minus B, A square minus B square is 1, and those kinds of elements, okay? So this is exactly the norm inside that quadratic extension. And I want to know whether, if it's surjective or what is the co-kernel. I'm interested in the co-kernel. So typically, the co-kernel is infinite. I don't know how to see that, like an obvious way to see that, but I looked up a paper, and that paper says, one of the conclusions of that paper is that this is infinite. So Yeah, I mean this is the L and Q are global, so this is not local, the class field theory map. It's a different map. So it's not Edels or something. Had it been Edels, it would have been surjective. So the co-kernel being infinite means that for a given GL2 conjugacy class, there are multiple, infinitely many SL2 conjugacy inside, sitting inside that. Are you following? Yeah. So there are. So this implies infinitely many O SL2 inside a fixed OGL2. And the property about these classes is if I look at the connected centralizer here, then it is connected, but it is anisotropic. So I denoted this by H. So the same H here is just trivial. And that is the same as the AG, which there is no center for SL2. And so these are the anisotropic classes. Okay, so this takes care of the first case here, that the characteristic polynomial is irreducible. Now the other case is that the next case is that it has distinct roots. So second is P has distinct roots. And say an element gamma, which looks like TT inverse, is in O. And since it has distinct roots, T is not equal to the identity or it's negative. All right, so the connected centralizer in this case is just M naught, because that is a centralizer of this element. Other elements also look like this, they commute. And in the final case, it's easy to see that this agrees with the GLN. So this class red inside GLN is the same as this class red inside GL2 and SL2, sorry. Yeah, that's what I mean, yeah. And the other final case is P has a unique root. So either 1, 1 belongs to O or negative 1 belongs to O. They're clearly not conjugate. And in this case, so H here is the full group SL2. No. Actually, it is a compact group. But if you take the sorry, H is the connected centralizer. Then you take the maximum split. So it is so H is it's a minor thing, but the connected centralizer is denoted as H. Then the condition of the lemma is that the maximum split torus of H is AG. So in this case, H is not identity. The connected centralizer, the torus split torus inside H is identity, because H is anisotropic. Thank you. Anisotropic. So no split torus inside H, and the split torus inside H is the same as the center of SL2, which is trivial. So what happens here? So H is SL2 is right. Yeah, okay. And if you look at either this element or this element, the O, so O in this case, or this case means this case, is known as the unipotent variety. Because it is the collection of all unipotent elements inside GQ. And it's a variety also. It's an intersection of closed sets. So it's a variety. It's known as the unipotent variety. And when Arthur goes on to prove these things, so you realize that these are the easiest classes and these are the toughest classes. And if you go from 1 to 3, it's the increasing order of difficulty in whatever Arthur does or whatever you have to prove. The anisotropic classes are easiest, and the identity ones, in this case, they are the worst, the maximum singularities in some sense. All right? Okay, so now our goal is to define the define J as a sum, define the coarse geometric expansion. So with that in mind, I define the anisotropic rational datum is a pair, the equivalence class of pairs P comma alpha, where P is a standard parabolic and alpha is an anisotropic class in MP. The Levy subgroup of P. So if the class is not anisotropic in G, there is a smallest class, smallest Levy inside which it is anisotropic, and so this is the Levy MP. And you say that two elements P comma alpha is equivalent to P prime comma alpha prime if they are conjugate. So if there exists an S in W AP prime. So these, I haven't defined this, but these are the linear maps from AP to AQ, AP to AP prime, obtained by restricting Weil group elements. From A0 to AP. So this is this set, and if I want that S should take AP to AQ such that if S should map WS alpha WS inverse. So WS is a representative of S, so it has to map P to P prime, alpha to alpha prime in some sense, and then they are conjugate. And if you define in this way, there's a bijection between O and these classes. So there is a bijection between anisotropic rational data and semi-simple conjugacy classes. Which are in further bijection with the Arthur conjugacy classes. And explicitly, if you look at a P alpha, then you send it to gamma S such that gamma belongs to alpha. Okay, so for SL2, in those three cases, what are the corresponding anisotropic rational data? So in the first case, P is irreducible. So in that case, it is anyways anisotropic. So this, the first case is just G comma alpha. And the second case, that P has distinct roots. So in that case, it looks like M naught, comma this TT inverse. And in the third case, it looks like M naught, 1, 1, or -1, -1. Okay, so these are the three types. All right, so now we will define the distributions JOF. Or before that, the KOF. So recall that, recall the definition of Kp. It was the integral over NPA of the sum over gamma in MPQ of f of x inverse gamma ny dn. And then you define KPO for O in O as the integral over NP, the same thing. And here you cut out with O. Here you cut out with O, and then you define this. So then you can write then you can write KOF, KOTXF as the sum over P minus one term something, the sum over delta of KPO something P hat of something. This is what you define. The usual things inside. You're cutting out with O here again, okay? So this gives you the KTO. Now, if you can modify the proof of yesterday so that this also converges in the same manner. There is some little work that Arthur does, but essentially the same proof carries out at most of the places. That if you integrate this over GA1 mod GQ, you get something finite, that this integral absolutely converges. In fact, when Arthur does it in the Duke paper, he doesn't do what we did yesterday. He just does it for these classes and gets done with it. Okay, so it follows from the earlier proof that integral of KTOXF dx converges absolutely. Okay, so now this gives you a formula JTF is sum over JTO F O in O. Now this is the coarse geometric expansion. So JTO is the integral of this guy. Okay, you add them up. This converges absolutely. You have an honest expression. This is known as the coarse geometric expansion. All right. So now, for some O's, not all O's, Arthur gives a more explicit formula. All right. And then for the remaining O's, he tries to modify what he got in terms of weighted orbital integrals and tries to get such a formula, a more explicit formula for every O. Okay, so first I will define what the special O's are and the corresponding JTO for those O's. Okay. X, what is the question? X, which line you want? The truncated orbital integral. Here. There's an X here. What is this integral over? It's GA1 over X in GQ GA1. Yes. Then X will go away, no? There's an X here, which is the X here and so on. So there is an x here, x here. This is Kp x delta x delta x. Yeah, okay. So one little comment here is that maybe we can talk after. Yeah. So one little comment here is that's the same proof that says these. Let me write it. So the invariance formula that we had holds for these JOs. And before that, these are also polynomials in T, and they can be extended to all T, or not just T regular enough. And you fix that special point T where the distributions become independent of the minimal parabolic subgroup. And so you define JO of f as the value at that special point T naught, O, f, and so on. So then again, this will also converge similarly and so on. So now the remark is that the distribution, so we had this formula, if you replace f with fy, where fy is just conjugation by y, then you had this formula, q containing p naught of jmq fqy, where fqy is a function on the mq, the levy of q, and so this came from a map from the functions on G to functions on MQ, and you evaluate this. So we had this invariance formula earlier. Now the same holds when you have O, except what does it mean for a class O in OG to be read inside MQ? We have to answer that. I mean, so the meaning of this is that there is a map, the obvious map from OMQ to OG. So what is this map? Take a Arthur conjugacy class in G, cut it out with MQ, that gives an Arthur conjugacy class inside MQ. On the other hand, if you take a conjugacy class here, pull it to the front and complete it, then that gives you a conjugacy class here. Okay? Are you following? And then this makes sense. This is well defined as a class in MQ. And then this formula holds. And one thing to note here is that if you take such an O, that it does not cut out here for every MQ, for every parabolic subgroup Q, that it doesn't cut here, then there is no contribution from such parabolic subgroups, right? And then in that case, the distribution is invariant. And those classes we called as anisotropic. It doesn't have to cut a parabolic subgroup, all right? So let me write what I just said. So if O intersect with MPQ is empty, then JO MQ is just 0, and these distributions are invariant. So those corresponding to the G, so recall in SL2 case, the anisotropic ones are the ones whose anisotropic rational datum contains G, it corresponds to G. And so those classes, these are the good ones. So these classes are good, these classes are bad, okay? So this you have to do more work. All right, so this is that remark. Now, let me define some special classes O, and for those special classes, a more explicit formula for this JOF. So two assumptions. The first is that O consists of only semisimple elements. that is this class, because this is the anisotropic class, satisfies this condition. And the second condition is O is unramified. That is, the centralizer of gamma, if gamma is in O, equals m gamma MPQ, where this MP is the correspondence between O as P comma alpha. So there is a bijection from anisotropic rational data to semisimple conjugacy classes, and a bijection from semisimple conjugacy classes to Arthur conjugacy classes. So through that bijection, I'm identifying these two objects. And then if given a P, there is this MP, and this is the condition. And also in our SL2 case, these ones satisfy this condition. So yeah, I will not write that, but these two conditions are met by such conjugacy, Arthur conjugacy classes. And for such classes, Arthur proves the following formula. The JOF is the volume, there is a volume term, sorry, in SL2 it is correct. And there is an integral So this is a weighted orbital integral. It is, the orbital integral is weighted by this weight, and there is a volume term and there is this orbital integral. Now this Vmx, so there is some combinatorics involved in the definition of Vmx. I will not have time to explain it, but I will just talk about it. Arthur defines the notion of a GM family, which means that in the simplest example, it means there is some, they have, let me draw a picture and then I will tell. I'm not going to explain what this VM is and what is the definition of the GM family, but I will give you a very brief idea of what is going on. So in the case of SL3, where you have this diagram, it means that you have functions indexed by in these chambers, and they have to agree on the wall and on these, and these. Okay, if they agree, then when you take the difference and divide out by this, then you get a finite thing. Fine. So in the SL2 case, if this is the origin, you have a function defined here and a function defined here, and if they agree on this point, so if you have f here and g here, then if you have fx divided by x, and then if you take minus gx divided by x, then it is well defined as at x goes to 0 also, if f and g agree on the common wall. Okay, this is the one-dimensional picture, but the same in principle this is. So the summary is that if you have functions indexed by the while group, and if they agree on the walls, then there is a common smooth function you get out of it, and the smooth function involves some cancelling of the poles at some points. Okay, so that is, if you are given a GM family, you attach it to a smooth function. I mean, you can attach a smooth function to a GM family. So in this case, there is a GM family that Arthur defines, and this is the smooth function corresponding to that. If you look at the clay notes, on the first page there is some hexagon here. That is the GM ortho, the smooth function. The characteristic function is this smooth function corresponding to the GM orthogonal set here. I don't have time to discuss that, but there is some very interesting combinatorics that happens here. And if you go to the spectral side, also the same GM family is used when he does the intertwining operators, and he has to normalize the intertwining operators and so on. But I won't have time to discuss that. Yeah, the centralizer of gamma inside GQ. Yeah, centralizer of MP. Yeah, centralizer of MP. Thank you. Yeah, centralizer of MP. So in the SL2 case, what does this formula tell us? It tells us the following. So for SL2, if you have O correspond unramified, this is the same as O is corresponds to this G comma alpha. So this is anisotropic. Okay, and in this case, this volume term comes out to be MPA1 gamma mod MPQ gamma is nothing but GA1 gamma GQ gamma, and this turns out to be HQ mod HA mod HQ. Where H was the connected centralizer of gamma. So this and H is compact, so H is anisotropic. So this, anyways, it has this quotient has finite volume, and in this case, it turns out that this is identity. This VM function is identity because M is G. So if you have G at the bottom, it's typically its identity. In this case, this is just 1, and this is the volume of HQ, HA mod HQ. So if you look at this formula, this is exactly the term appearing in the co-compact case. Okay, a typical term in the co-compact case looks exactly like this. That is the offshot of this. The simplest terms look like the co-compact case. All right. So now the objective of Arthur is to define such explicit orbital integrals for O's which are not unramified, for all other O's. And so he defines what is known as the weighted orbital integrals. I will define that. So using these weighted orbital integrals, we will have a more explicit formula for all JOF. So one reduction is that if you have a function f in C infinity C GA, then there exists a finite set of places containing the Archimedean ones, such that if you go outside them, then the V component at that place is just the characteristic function of the maximal compact subgroup at that place. Let me write what I just said. Actually, F is a finite sum of such functions. So there is no loss of generality in assuming FP, FV. Let me write FV. Sorry, what? Oh yeah, which are anisotropic. Does it follow from here? No. Wait. It is automatic, I think, right? If I look at, they have to satisfy this condition also. O consists entirely of semisimple elements. Yeah, but in SL2 case, it is just TT inverse case, right? Anyways, but I don't have any harm in adding this, but so. Okay. Anisotropic. So your TT inverse does not consist of entirely semisimple elements. Yes, you're right. Yeah. Yeah, you're right. Yeah. It has in the first case, so G comma alpha, this condition is needed. Yeah. Thanks. So here there is a finite set S such that if V is outside S, then the V component is just the characteristic function of the maximal compact subgroup at that place. And so you can think of F as sitting inside C infinity C Q of Qs, because you just ignore the other places and it will be just a characteristic function. They are not so exciting, so we just keep them aside. And then so here Qs is the product of V in S, QV, VP, whatever. So Arthur defines the weighted orbital integral as follows. So for unramified O, Arthur defines the weighted orbital integral as Jm gamma f this formula actually is not true, but this holds for those classes also, so T inverse. But we can discuss that later. Actually, this also is unramified, I think, because in this case the quotient also is. Yeah, we can discuss that later. Yeah. So suppose you have unramified O corresponding to P comma alpha, the anisotropic rational data, and this is the weighted orbital integral x inverse gamma x Vmx dx. So this is the definition of the weighted orbital integral. This is the wild discriminant. I don't want to define it. And now using these objects, you write the JOF in terms of these objects. So what Arthur does is, if you have a set S of places, then what you do is Arthur writes Jm gamma f in terms of Jm gamma v fv using the GM family identities. And so inherently he says that this Jm gamma f, you can think of them as a local, so local objects. Now what happens when the class, if you look at just this expression Jm gamma f, if O is not unramified, then this doesn't make sense. But let's see, if you take gamma to be the identity element, then this integral diverges, Vm doesn't make sense, and so on. So say if you have 1, 0, 0, 1 identity element inside O, then this is the unipotent variety, and it doesn't make sense. So what Arthur does is consider the integral Jm of AF, where A is, he wiggles, so T inverse, where T is not plus minus 1. T is not the identity, then this is well defined, okay, for those Levy. And then you want to take the limit as a goes to 1, but the limit does not exist. But if you add a factor, then the limit exists. So, so what Arthur says is that Jm of 1, in our case of SL2 actually, so if you think about SL2, Jm m0 of AF, you have to add a function R0 G A Jg of AF. This is well defined, and the limit as a goes to 1 is also well defined. And so it defines this Jm of gamma m0 of gamma f as this limit. And in the case of SL2, you can explicitly compute what this function is. If you start with a this, and this is log mod t to the minus 2 minus mod t to the 2. This is this function. And in general, he says there exist functions like this, where this always, you can add these terms and this always makes sense. So the general formula for this J, the weighted orbital integral, he says there exists such functions. So let me write that theorem. There exists functions R, M, L, A, F, no, A, gamma, such that Jm gamma F is the limit as a goes to 1. So just as we have this, these two sums here, you have such functions RML such that this sum makes sense as a goes to 1. And for every gamma now you have this weighted orbital integral. And here Lm is the set of Levy subgroups of standard parabolics with Levy subgroups L with L containing M. So this is the definition of Jm. Now I will just write down the statement for the fine geometric expansion and only look at SL2 and what that tells, and explicitly we will try to write all the terms for SL2 in the case of the fine geometric expansion. So actually, I don't know what the A restriction is. I see. Okay. Okay. This. Gamma is in O. M is P, M, MP, NP, and the P is this. Yeah. I mean, this condition implies this condition. So this condition implies one inequality. This condition implies one inequality, and then you want equality in that inequality. Okay, so the theorem here is that for any O, there exists a set SO containing the Archimedean places, such that if you go bigger than that and take your test function inside this Q set of places, then the following holds. So you have the expression for JOF as a sum over the standard Levy subgroups of G of while group, size of the while group, gamma, and this is the this object I haven't defined, I will talk about this very soon. This is the MS equivalence class of AM S gamma JM gamma F. So this is the fine geometric expansion for every O. I will explain what this MS equivalence class is, and I will talk only about the SL2, and we will try to compute everything explicitly for SL2 in this setting. So in the first case, if O is the so this is the MS equivalence class. So if O is the unipotent variety, which means the identity belongs to O, so you denote it by U also, then GS equivalence class just means that conjugacy over GQS. Now, if you take these semi-simple elements 1U01 and you ask if they are conjugate with 1V01 inside SL2, what is the condition? Can you tell me what the condition is? The condition is that UV inverse, so let me write Q here, is a square, yeah. Yeah. So although note that if you take the index of Q star square inside Q star, this is infinity. But if you put, even if S is non-empty, if you have a single place also, then this Q star S is square is finite index in Q star, QS. Okay? So if you impose a local condition here, then you get finitely many classes inside this O equivalence. Okay? Typically there are infinitely many these classes, but if you impose this condition, this is a finite set. All right? Now let us discuss the three cases. First case is O is anisotropic. So in this case, M has to be, there are two options for M. M belongs to L, and this L is either L of M0. This set is either M0 or G. These are the only Levy subgroups. So if M is M0, then M0 of Q intersect with O is empty, because O cannot intersect any parabolic subgroup, proper parabolic subgroup, because O is anisotropic by definition. So there is no contribution from the M part, and so whatever you have is the G part here, GQ intersect O. GQ intersect O is just O. And in this case, you have just one term, JO of F is a G S gamma JG gamma F, just one term in this case. And I don't have time, but these two terms correspond exactly to the co-compact case. This is the volume term, and this is the invariant orbital integral. You have to see that this integral is actually invariant, but this is just a co-compact case setting, so directly it is invariant from that. In the second case, where O corresponds to the TT inverse, this element belongs to O for T not equal to 1 or minus 1. In this setting, there are honestly two terms. So MPQ M0Q will intersect O so if I call this element as sigma, then the sigma is the intersection, and GQ also will intersect O in O, and so there are two terms in that. So the JO F for this case is AG S sigma JG sigma F. This is the part for G, M Levy subgroup equal to G, and for Levy subgroup equal to M naught S gamma sigma J M naught of sigma F. And in the final case, when you have the identity, O contains the element 1, 1 or 1 minus 1 minus 1. In this case, so O is the unipotent variety. And in this case, there are some non-trivial objects here. So MQ intersect O. Again, you have two terms. So MQ intersect O is just the identity, and GQ intersect O is just the O, the unipotent elements here, and this O is just the U, and UMS, UGS, because M is G in this case. So UGS, I haven't defined what MS-GS equivalence classes are, but the definition is technical. But for such UGS, the unipotent variety, the definition is easy, and it just says that gamma 1 and gamma 2 are GS equivalent if they are conjugate. So here I wrote that, yeah. If they are conjugate over GQS. So this will be a finite set. In general, this is infinite set, but when you take this conjugacy, you get a finite set. In this case, the expression for JUF, U is the unipotent variety. It consists of these finitely many terms UGS, AGSU, JGUF, plus the Levy terms, and there is only one term. Oh, there is a half here. Yeah, it will flip also. So maybe that's the 2 here. I will get 2 terms. No, I will get 2 terms. But I don't know if they are conjugate also. Okay, that also I have. Sure, yeah. So this T inverse T also will be in that. I have to think whether they are in this conjugacy or not. I haven't checked that. So I will put a star here. I don't know actually. Right now I haven't thought of that. But there is some half term here because the size of the while group here is 1/2. So that is the half contribution. Yeah. You will have 2 elements. Yeah, you will have 2 elements plus another one half. Yes, you're right. Yeah, A M naught S sigma prime. Yes. You will have 2 elements. Yeah. So S sigma prime J0 of sigma prime F. Yes, you're right. There's no star now. Yeah, you're right. Yeah, there will be 2 elements here, and there will be 2 terms here. And in this case, I will have half AM S comma 1 JM 1 comma F. And for some elements, there is more explicit description of this. For example, when U is 1, you get the volume term, and J, this is JG is there is some more explicit terms. In general, you don't know what those AMs are, these elements, but in some cases you know them more explicitly than other cases. So I think I will stop here. Thank you.